Have you ever wondered how we can predict a future number? It might sound like a complex puzzle, but it is something we do all the time. We guess how long a trip will take based on distance. We estimate how much a grocery bill will be from the items in our cart. Regression is the formal name for this kind of prediction. It is a fundamental tool in data science. We use information we already have to make an educated guess about a number we do not have. This turns data into decisions. The core idea is beautifully simple. We look for relationships between things. Does more advertising spending lead to more sales? Does a larger house usually cost more than a smaller one? Regression confirms and quantifies these relationships. It gives us a mathematical formula, a model. Take a known value, like house size, and get a predicted value, the price. It finds patterns hidden in noisy everyday data. Simple lines and curves can unlock powerful insights. By the end, you will understand the building blocks and be ready to explore. Let us begin by looking at linear regression. Imagine you have a collection of data points on a chart. They might look like a cloud of dots. Linear regression is the art of drawing a single straight line through that cloud. This line is not just any line. It is the best possible line, the one that comes closest to all the points at once. It represents the trend in your data. It shows how one thing changes on average as another thing changes. This simple line is surprisingly powerful. It is often the first model a data scientist will try when faced with a new prediction problem. This best fit line is defined by a simple equation. You might remember it from school. I equals mx plus b. In our world, m is the slope. It tells us how steep the line is. For every 1 unit increase in our input x, the slope tells us how much our predicted output y will change. The other part, b, is the intercept. This is where the line crosses the vertical axis. It is the predicted value of y when x is equal to 0. Together, the slope and intercept give us a complete model for making predictions. Finding this perfect line is a mathematical task. The algorithm searches for the slope and intercept that minimize the overall error. What is the error? It is the vertical distance between each data point and our line. Some points are above, some below. The line tries to balance these distances. It aims to be as close to as many points as possible. This is how a linear regression model learns from data. Because once we have this line, we can make predictions for new data. If someone gives us a new x, we use the equation to find y. This is the essence of prediction. Let us make this more concrete with an example. Imagine you are a real estate analyst. You have a data set of recently sold houses. For each house, 2 key pieces of information: living area, size in SQFT, and the price it sold for. Your goal: predict the price of a new house given its size, a perfect scenario for linear regression. First, visualize the data. Create a scatter plot. X-axis, living area. Y-axis, price. Each house is one dot. If our hunch is correct, bigger area generally means higher price. Visual confirmation matters. Now fit the line. The algorithm looks at all points and finds the optimal slope and intercept. Example: slope plus $150 per SQFT. Intercept $50,000 baseline. Predict for a $2,000 SQFT house. Plug into y, phrase mx plus b to get an estimate. This gives a data-driven starting price. Models are not perfect. Other factors: location, age, condition. The line is an average trend. Some houses sell above, some below. The difference is the residual. Measuring that error is the next critical step. R² and MSE will help us tell if predictions are good. A straight line is a wonderful tool, but the world is full of curves. Sometimes the relationship is not linear. It might start slow, speed up, and then level off. A little fertilizer helps a lot, but too much stops helping. It can even harm the crops. Fit a straight line here and the model underpredicts in some areas and overpredicts in others. This is where polynomial regression comes to the rescue. We create new features from x, x squared, x cubed, and run a multiple linear regression in this expanded space. Plotted back, it becomes a curve. The degree controls how curvy the line can be. Degree 2 makes a parabola, degree 3 can make an S-shape. Flexibility comes with caution. Very high degree risks overfitting. Memorizing noise, not learning pattern. Consider engine power versus fuel efficiency. Very small engines may be inefficient. Efficiency improves, then drops for very high power. Plot horsepower on X, mpg on Y. We will likely see a curve. The dots rise at first and then fall, an upside-down U. A straight line would miss that efficiency, decreases for very powerful engines. A degree 2 polynomial is ideal. Add horsepower, fit the curve, and capture peak efficiency in the mid-range. Choose a degree just complex enough to capture the trend, not so complex that it chases noise. That balance between bias and variance is what we want. Once we have built a model, linear or polynomial, how do we know if it is any good? We need objective metrics. Metrics tell us how close predictions are to real values. Three common ones are MSE, RMSE, and R2. Mean squared error. Compute the error for each point, square it to punish big errors, then average. Lower is better. Units are squared. Root mean. Squared error is simply the square root of MSE, bringing units back to the target. Predicting house prices. An RMSE of $20,000 means predictions are off by about $20,000 on average. R2 tells us what proportion of variance the model explains. Typically between 0 and 1, but can be negative for poor models. Higher is better. R2 of 0.85 means the model explains 85% of variability. Metrics are essential, but they do not tell the whole story. Numbers can sometimes be misleading. Always plot the data with the fitted line or curve to sanity check the fit. Residuals should look like a random cloud around 0. If you see a curve, a funnel, or clustering, it is a red flag your model is missing structure. Learning curves diagnose bias and variance. If both errors are high and flat, high bias. If there is a large gap, low training error, high test error, high variance, and overfitting. These visuals are not just for presentation, they are core diagnostic instruments for building better models. Seeing the concepts is one thing, but seeing the code makes it real. With scikit-learn, building these models takes very little code. Python comment, simple linear regression in scikit-learn. From scikit-learn.linear model import, linear regression. Create the model, model, cas, linear regression. Train the model, model.fit, x, train, y, train. Make predictions, y, pred, model predict, x, test. For polynomial regression, add one step, Python comment, polynomial regression in scikit-learn. From scikit-learn.preprocessing import, polynomial features. Poly chucked polynomial features, degree 2. X polytrain, chucked poly.fit, transform, x train. Fit linear regression on x polytrain and y train. Transform x test, then predict. Try it yourself. Find a simple data set, car prices or fuel efficiency, load it, split it, run a few lines, and visualize. We have traveled a significant distance in a short time. We started with regression as a tool for predicting numbers. We explored linear and polynomial regression and learned to be cautious with complexity to avoid overfitting. We demystified MSE, RMSE, and R2 and saw why visual checks are essential. Your simple workflow, concept, code, results, is the cycle you will repeat throughout your data science career. Start simple, stay curious, practice. The world of data is waiting for you to uncover its patterns. Think of this as a friendly first step into predictive modeling. See you on day 13.